Dear fellow coders, welcome to One Little Coder. This is day 10 of Kaggle's 30 Days of Machine Learning Challenge. If you are new to this channel, this is a channel where I make programming or coding tutorials focused on data science and machine learning. So let's get started with what we are going to learn today. So in the previous section, what we learned is we learned to build a first machine learning model, and we also learned how to evaluate our machine learning model. So if we have built a model, how are we going to evaluate? So now, as part of the previous section, if you had attended, like if you had watched the entire video, you would have noticed that I used a word called overfitting. I didn't expect that this is going to come, so I just started giving you a little bit of introduction about overfitting. So this section is particularly going to focus on underfitting and overfitting. If you want to read more about this statistically, I would suggest you to read about a concept called bias variance trade-off. Let me just quickly show you, then we can move forward with the section that we are trying to deal with this. So if you want to, like in the similar subject, but if you want to learn more about how things happen, you should definitely look at bias variance trade-offs. So this is something that a lot of people usually ask during interviews also, like what is bias variance trade-off, how do you handle underfitting, how do you handle overfitting. So all these things usually come in interviews as well. So you might think that this may not be very important as building a model, but this is quite important in building a quality model, and it's also quite important in you actually trying to set up a good modeling setup, like good model prediction, all these things. Okay, now let's begin with underfitting and overfitting. Now imagine that you have built a model and then you know how to measure the accuracy. And in the last video, we learned that the model that we had built, which is a decision tree regressor, had a terrible accuracy. So I think if I remember correctly, we had about $25,000 of MAE, mean absolute error, which is usually not very acceptable. So what do you do next? So one of the things that I said is maybe you can experiment with a little bit of more features like columns, and then you can try. But what if you want a different option? So a different option is always to go for a different model, a model that could fit the training data in a much better way than what we used. For example, if you use something like a linear regression, which is like a very basic model, there is a high chance that if you use something like a decision tree might give a better result than linear regression. So you can always test this. So the same way, if you think decision tree was not giving a good accuracy, then you can enter into a new world of models. So in this section, we are going to learn about overfitting and underfitting, and we are also going to learn about random forest. Quickly, we are going to see random forest in the next section. So now, if you want to look at more options, different models, you should look at all other options. But what if you want to use the existing decision tree and then you want to improve it? So one of the things that we learned about decision tree is that you have something called split. So every time you have split, you can see you have a node and then it gets split, and then you have leaves. So node gets split and then you have leaves. So we learned that as much as the decision tree grow bigger and bigger, there is a good chance that your model might have better accuracy. More number of splits, better accuracy. But with more number of splits, which leads to tree depth, with more number of splits, also with more number of tree depth, you would face another problem. What? The problem that you would probably face when more number of tree comes in is that let us imagine for now that you have got 10 splits. So when you have every group gets split into two. So if you have 10 splits and every group gets split into two, so you will have 2 power 10, which is like around 1024 leaves at this point. So you know that at this point it's going to try to learn as much as granular as possible and then give you the result. So what I'm saying is, imagine like you have only 2 houses in this group. So first split will happen and then you have 2 houses. But imagine now you have 4 houses. So first split will happen. So now it's going to split your entire 4 houses into 2 groups when it wants to learn, and then within these 2 groups it's going to see this condition and then it's going to split further. So at your leaf, so basically at 4, when you have 4 number of houses, it's going to learn from each house and then it's going to give you the prediction. But the problem now is, in the previous section we also saw one important thing, which is what if you have greenhouse and then that greenhouse in your training data always had higher rate. So that greenhouse has nothing to do with price. Basically, that greenhouse nothing to do with price. But what if your model, because you try to build more deep trees, it's going to learn that, oh, maybe whenever I see greenhouse, I actually has more price, so that is going to be one of your split, but it doesn't actually matter in the real world. And this kind of problem where you try to fit your model as much as possible with higher accuracy in your training data, and you do not have enough data. Let's assume that you do not have enough data as well, so every granular characteristics of your training data becomes one of the predicting split, like value, the rule on which the split is going to happen, which means your model might have a very good accuracy in your training data, because it might say, oh, do I have a green door? Probably it's going to have higher value, and your training data might validate that assumption, and then your accuracy on your training data might look good, but in the real world data it might have a terrible experience. And this phenomenon is what we call as overfitting. Why? Because when we divide the houses that we have as many as leaves, like if we have all the houses as leaves, then we might have fewer houses in each leaf, which means our prediction might be as close as possible to the original value that we have got. But the problem is, in this case, our predictions are going to be very unreliable in terms of new data, because what we have done is we have tried to make prediction based on every few houses that we could, which means the noise that is available in these few houses is something that our model might have learned as a signal, which may not generalize well in the real world. So generalize is the keyword that probably mostly when people ask you questions about this thing, they would try to identify. So our model may not generalize well in the real world, and that is what we call as overfitting, because our model has tried to fit more and more, overfit the data, where even when the signal does not exist, so it takes the noise and then tries to identify as signal. So overfitting is the phenomenon where a model matches the training data almost perfectly, close to 100% accuracy. If you remember, I told you 100% accuracy is almost like a curse. Whenever you see something like that, you should always be aware that there is almost highest number of likelihood that your model is overfitting, but it does poorly in the validation and new data. On the flip side, now you might say, dude, let's say that I don't want to overfit. What if I just stick with only single split? You know the reason, why did we even start splitting into more? Why did we start giving more attributes? When you have very less number of split, when you have very less amount of split, what it might do is it might actually underfit. It might not predict well. Imagine you have only based on only one attribute you're going to split, which is, let's say, number of bedrooms. If you're going to split based on number of bedrooms, now your data, your price range might vary from $140,000 to $233,000. So basically you're dealing with almost $90,000 spread, which means there is a high chance that your model might not do a correct job, or in fact it may not do a correct job. So that is called underfitting. So when you do not have enough split, or when you do not go deep enough with decision tree, especially, your model might not learn enough. So the training may not happen enough, the fitting may not be enough, that your model may not be able to learn the signals from the training data. It might even miss the existing signal from the training data, and that's what we call as underfitting. So what is underfitting? When a model fails to capture important distinctions or patterns, especially say that signals from the data that is useful for predicting the predictor variable, so it performs poorly even in the training data, and that is called underfitting. When it performs super awesome in training data and then it does a terrible job in testing or validation data, that's what we call as overfitting, because the model has captured noise as signal. And when we see model has performed poorly in training data itself, which is it is not able to learn the existing signal, that's what we call as underfitting. Now, to just visually represent underfitting and overfitting, imagine your x-axis. This is your tree depth, when you grow the tree, this is how it is, and this is your measurement evaluation metric, MAE, in this case mean average error. So now what are we going to call as underfitting? when our error is huge, error is very high, even in both training and validation data, then we call this underfitting. So both training and validation data, our error is terrible. Like imagine like your error is terrible in your training data. Why would you even check it against validation data, right? So this is what we call as underfitting. Now, when you grow the tree with more deep number of splits, your model might have the highest accuracy, which means error has dropped. Highest accuracy means error has dropped. So because this is error, when this is going up, which means accuracy is low, when it is coming down, accuracy is high. So which means for training data with more number of tree depth, your error might be very low, very less, which means your accuracy is highest. But on the other hand, because your model has started overfitting, your validation accuracy might be terrible. So it may be like as close as how you do underfitting. So basically there is an inflection point after which your model would start overfitting. So basically there is an inflection point after which your model would start overfitting. And if you visually see, just think for a moment yourself, when you visually see this graph, can you identify what that inflection point could be? Like if you see this graph, somebody tells you that there is a point, after this point my model starts overfitting. Can you guess what is that point? Okay, let me give you a second to guess. If you have not guessed at this point, you can assume that in this inflection point, the point where you can assume that overfitting starts is the point when your training accuracy goes up, which means your training error goes down, but your validation error goes up. So let me repeat it again. This inflection point is the point where your training accuracy training accuracy goes up or training error goes down, but your validation error goes up. So your validation error is going down. At one point it would start going up again, even when your training error is coming down. Let me repeat it again. This is your error, this is your training error, and this is your validation error. So usually as you increase the tree depth or whatever you do, your training error would come down. At the same time, your validation error would also come down. But there is an inflection point where your training error would come down, but your validation error would start going up. And now you know that this is the point where it starts overfitting, because your validation data, your model performs bad in validation data, started to perform bad in validation data, but it still thinks that it is doing a great job in your training data. So this is the point where you need to stop training so that your model has the highest training and validation accuracy, but it is not overfitting. Okay, I think that's too much of an explanation. So let's get started with the code. Now, when we talk about decision tree regressor, how do we increase the tree depth? We can increase the tree depth in a few different ways. So the way we can do is by defining maximum number of leaf nodes that we want to have, like the maximum number of leaf nodes that we want to have. So that is a way for us to control the tree depth from overfitting and underfitting. So now this code that we have, what we are doing is, if you are familiar with the previous classes, we are first defining a function. We are defining a function which will help us create this kind of chart. So basically what we are saying is, calculate mean absolute error for the given tree maximum leaf node. So as you increase this, give me the value of this for both my training and validation accuracy. And that's what this code is doing. So get MAE, mean absolute error. One of the argument is the leaf node that you are trying to pass on. Then you want to get the you want to send the training and validation data set, and then you are going to fit a decision tree regressor like we did in the previous video, and then we are going to fit the model, predict the value, and then calculate mean absolute error, and then try to plot it, something like this. And that is what we have tried to do in this case. So now we can use a for loop. After we have this function, we can use a for loop and then pass different data. Like 5 is the maximum leaf node. Leaf node, if you do not remember, this is your leaf node. It's like the node, the top somewhere. This is your leaf. So now you can say 5. So which means 5 will go here, and then 5 is set as a parameter here. So model will maximum try to have only 5 nodes. So you can see 5, 50, 500, 5000. As you start increasing the value, you can see your mean absolute error going down. So you can see, as you can see, when you start when you look at this mean absolute error, it goes down. But you can note a point where your mean absolute error starts going up. Did you see? Here it goes down because this is a validation error. Like if you remember, this is a validation error. You're predicting with validation data set. So it is going down and suddenly it started going up again. Like if you see a graph like this, it would go like this. So here is your inflection point, and that inflection point in this case is for us 500 nodes. So you can see, as we have increased number of node leaves massively, our model starts overfitting. That's why your mean absolute error started going up as opposed to going down. Okay, because this is validation data, and that's how we're going to validate. So now what is the conclusion? The conclusion is quite simple. So overfitting captures spurious patterns, which is like noise. So it's still a pattern, that's why it's trying to identify. It's like green color, like door. Imagine like if you're trying to predict laptops, and then you use a lot of Mac machines, and then you use some Windows machines. Now every Mac machine might have aluminum, right? So now what you might start thinking is, like, whenever you see aluminum, so your model might say, oh, I've seen aluminum, so it's probably a computer, which is a Mac computer. Now imagine, like, now you have got an aluminum utensil. Now overfitting is like your model is going to say, whatever is aluminum, I'm going to say it's a Mac machine, even if it is an utensil. So that is the problem. So now it is called overfitting, so which leads to less accurate prediction outside your training data, usually like validation data, test data, real world data. What is underfitting is your model does a terrible job even capturing existing signals, relevant patterns, and it might also lead to less accurate predictions. So if you want to read more about it, like I said, bias variance trade-off is an important area that you should read, especially if you're going to appear for an interview in for data science interviews. There's a very high chance that somebody might ask you, how would you prevent overfitting, how would you prevent or handle underfitting, what is bias variance trade-off, what kind of strategies that you might use, which models handle overfitting, which model doesn't handle overfitting. So this is typically people try to ask, and then get some answers from you. So just remember this area. So one of the reasons why we use validation data, which is not part of our model training, is to just evaluate these things, so that we can actually validate against validation data and then know what is that inflection point where we need to stop training. Okay, now that we have learned about underfitting and overfitting, let's turn towards an exercise. The exercise is loading. The moment you click it, so you are forking the kernel, or I should say forking the notebook. So Kaggle notebooks used to be called as kernel, and that's why the machine is getting started. Let's run it. So this is almost like similar like what we did in the previous sections, videos, classes, days, whatever you would like to call it. We have pandas for data frame manipulation, mean absolute error to calculate the evaluation metric, train and test split for validation, decision tree regressor, which is our model, read the data set, create y and x, and then start making validation errors, calculate validation predictions, and then calculate mean absolute error. So now our validation MAE, mean absolute error, is about like $29,000. The reason I'm using dollars when I'm talking about this is because this mean absolute error, so we know it stays the same unit. You don't have to necessarily say, but converting into dollars will help somebody visualize it, like mentally visualize it better. Now create the function that we just saw, which is going to help us in figuring out overfitting. Okay, now compare different sizes, 5, 25, 50, 100, 250, 500. What do we have to do? We have to write a loop for node leaves leaves in candidate max leaf nodes, get MAE of leaves and we have to pass on the training and test data as well, which comes from here. So I can probably pass the same thing because we have already created it here. So we can basically pass the same thing. Oops. Okay, and then print the value. We can print, and then we need to store the best tree size. Write a loop to find out the ideal tree size first, and then store. Okay, so I'm going to run this as a separate code. Oops, did I make a mistake? Okay, there's a comma and there's. Okay, so now you can see when you look at this thing, it's reducing, and at this point it started going up. You see, so it is coming down, 272, coming down, and again it become 282. So now you know this is your inflection point. And what is the value? First, second, third, fourth. So first, second, third, fourth. So when it is 100 nodes, then you know that it is doing good. Okay, so when it is 100 node, it is doing good. So we can say 100 and then run this. Did I just store the best value of maximum leaf nodes? It will be either 5, 25. This store the best value. So how do we find out what is the best value? The simplest way, invalid syntax. Why did it say invalid syntax? Okay, again, I don't know why did I put this comma. So I think I'm making a mistake. Okay, when you run this thing, it says correct, but this is not the right way to store it. Like, I'm manually looking at it and then doing it. What is the best way to do it? So what you can do is you can create a validation MAE as an empty node. Okay, and then in every loop, every iteration, we can store that value, validation MAE dot append. So we can store the value. So what would happen if we do this thing? When we do this thing, you can actually print validation MAE, and you got this thing, and min of this, you got the minimum value. Okay, you got the minimum value. So now what you can actually do is basically you can actually create a dictionary. I think that would be better. So you can start adding like this equals the node, which is in our case leaves. Okay, if we do this, when you print this, what you see, you would see a dictionary of every node and then the minimum value. For the easiest way for us to figure it out, let's go say find minimum key in Python dictionary. Okay, when you search for it, most likely you would get a Stack Overflow answer. You got an answer. Okay, you know, like this is the best. You want to go inside and read it, you can read it, but let's try it out. Where is this? So this dictionary, it says this, but what we want is this, and then we want t.get. When you run this thing, it says 100%. So now what I'm going to do is I'm going to say this is going to dynamically give us the minimum value all the time whenever we want, and I'm going to paste the code that we tried here, and then I'm going to paste this code that we tried here. Let me remove this cell, otherwise it might confuse. Where do I paste this? I paste this here, and oops, run it. It says correct, and if you want, you can actually print this, and then you can see the entire thing. You can even print the entire value. So basically what we have done is, instead of manually copying and pasting that 100 node, we have created a dictionary which will always put the MAE inside the dictionary with the number of leaf as the key. So key and value, and we try to figure out the minimum value from this, which would check the value and then get the relevant key, and which is 100 in this case. Quite a long answer, but you can still put 100 and then solve this problem, but I think this is good for you to know slightly more. So fit model using all data, you know the best tree size. So if you want to deploy this model in production, so you need to make sure that you would make it even more accurate by using all the data and keeping the tree size. Now that you have figured out what is the tree size, so you can actually build a decision tree model with that tree size. So let me repeat it again. So we wanted to find out the best number of leaves value parameter. This is called hyperparameter tuning. So we wanted to calculate the best value for this, but after we do that, we are not going to use the split, because now we know that this is the inflection point where our model has performed best. So what we would do is, now we would use the entire data and then start using it. So where is our entire data? Our entire data is X and Y. So what I would do now is go to the final model and say X and Y. Is that correct? Is that what we are supposed to do? We don't want to give this. Oh, sorry. We have to first define. What am I even doing? We need the column name, which is max leaf node, and we know the value of it. We know the value is equal to, we can say, best tree size, and add the best tree size here. So we have the final model. Now we can fit the final model X, Y. I have made some error. Correct. So we have predicted X and Y with the best model that we have got, and the best model we got from this thing. This process is usually called as hyperparameter tuning. You would see a lot of tips on the internet how to do that. So the next section, we are ready for the next section. We are going to learn about random forest. So let me save this, come back, then learn about random forest. Now this name might look familiar to you. Why? Because we just dealt with trees at this point, and then now we are going to talk about forest. Now, what is a forest? A forest, it is what is a forest? A forest is a collection of trees, right? So the same way, your decision tree has a problem. And what is the problem? The deeper you go, the decision tree will start performing poor, because it cannot it will start overfitting. And the shallow that you have the tree, it will start performing poor because it is underfitting, it cannot capture. So now to solve this, there are many solutions, there are many models, but one of the most used model in this category is called random forest, which is called an ensemble model, which means like you combine a lot of models and then you build this model. So now you actually create a lot of trees, and then you combine all these trees in such a way that you get the best accuracy. That's what basically random forest is. Now you build a lot of trees and then make a prediction by averaging the predictions of each tree component. So if you have a continuous variable, which means if you are doing regression, if you are trying to predict the numbers, you would average out all the predictions, so which means you have the least minimum error. Or if you are doing classification, then you would do something called voting, which is like majority voting. Let's say you have like 100 nodes. Out of that 100 nodes, 100 leaf nodes, and out of that 90 says like this email is spam, 10 says this email is not spam. So you would now take spam as an output because it is 90 majority. So there are a lot of voting strategies, but usually majority voting, and then you get the result for the random forest. So instead of building one single tree, you build a lot of trees, and then you try to average out or minimize the error, and then you get the output. And you might think, why the name is random? It is random because every tree that is built is a random sample of the training data. Every tree that is built, like if you, let's say like you have like 200,000 rows, it's like 2 lakh in Indian figure, 2 lakh rows. Then every time you would get a different sample of the number of rows, because that's what makes it random, and that's how it avoids overfitting, because every tree is different from each tree that is pre-built, because now it's a random sample, and then ultimately when you combine everything, you get a much better model. So you have already seen this code quite a number of times, how to do data loading. If you want to see the code, you can again see. We have pandas to read the CSV. You have a file path, and then you read it, and then you drop the missing values, and then you calculate the target Y variable, and then you want X. For that, you define what features you want, and then you use train and test split to do cross validation. You have split it, and then you have successfully saved it under train X, validation X, train Y, validation Y. Now what we are going to do is the same way we got decision tree regressor, we are going to get random forest regressor. So every time you are going to get this, always good to go to scikit-learn documentation, and then just quickly glance what they say about it. Scikit-learn, so as I said, it comes from Ensemble. So you can see an example which is from scikit-learn. Instead of tree, it says Ensemble get random forest regressor. Now what do they say about it? So a random forest is a meta estimator that fits a number of classifying decision trees on various subsamples. Sample is like random, okay. Subsample of data set, and uses averaging to improve the prediction accuracy and control overfitting. I think that is enough for us to learn. So the subsample size is controlled by max samples parameter, and if bootstrap is equal to true, but which is by default true, otherwise the whole data set is used to build each tree. Okay, now going back to random forest, we know we are doing sklearn.ensemble random forest import, sklearn.metrics mean absolute error import, then forest model. So usually people don't call it forest model or anything. There's a chance that somebody would probably call it a model, and then you have model, and then you can say, okay, when you have random forest, again, like we have already spoken about this thing, whenever you deal with random variables inside the computing environment, it is very important for you to set seed value. So this is kind of setting that random state, so that when you want to replicate this thing, you get the same output. So now you are going to fit it with the training data. That's what you're doing. Like I said in the previous section, scikit-learn API is quite good, which means you follow the same model, define the model, fit the model, predict the value, and then evaluate. That's it. It's the same set of steps. So any modeling you use, mostly you would see the same template. After that, you predict it with validation x, which is like the variables, and then finally you calculate the mean absolute error. And the mean absolute error we have got currently at this point is 191,000 for Melbourne housing prices. So now the conclusion is, so in decision tree when we got around 250,000 error, and with the random forest we have minimized that error about like almost like $60,000. So we have actually made a better model with just making one line of change. So that is why modeling is usually easy. You can always find these codes. What is difficult is knowing when to use what and knowing the nuances like overfitting, underfitting. So nobody is going to ask you, I mean, like some interviewers might still ask you, would you like to show me writing a random forest? People might still do that. They do this thing. But what questions you might ask is like, what is random forest? Define random forest. How is random forest different from decision tree? When would you use random forest? When would you not use random forest? And what are the parameters in random forest? How would you do hyperparameter tuning? How would you do cross validation? Is this the only cross validation you know? So these are the questions that you would ask, and these are the questions that you should prepare when you look for an interview. And not just for interview, while you are learning itself, it's very good for you to learn this thing. And my explanation of random forest could be quite naive. There are a lot of good tutors on the internet, like the channels that teaches you the in-depth calculations and math behind random forest. You should definitely look at some of those channels and then get to learn random forest more, because that might help you in making somebody understand, whether it could be your interviewer or your business stakeholder. It's always good to have that kind of understanding. So now we can get started with the exercise, but one important thing that we would like to highlight is random forest is one of these few models like XGBoost, which stands for extreme gradient boosting. This is like one of the few models, or like highly popular models, that work really well without even hyperparameter tuning. Without even you tuning the parameters, random forest would work really good. It would do a good job. So let's start with the exercise. It's loading. I hope I can finish it off sooner so I don't take a lot of time of yours. As usual, the disclaimer is exercise is something that you should do it yourself. So even if you watch this video, stop at this point, do your exercise. If you're stuck, come back here and then see that. So we have a predefined code, import pandas as PD for data manipulation, metric mean absolute error, train test split for cross validation, decision tree regressor, which is something that we used for decision tree. So now, oops, did I run this? Yes, it started to run. So we know when we do not split the best mean absolute, when we have not set max leaf nodes, our validation is this. When we set the best value of max leaf node 27,000, so you can actually see how are they specifying it, which is by like hard coded 100 value. Okay, so now this is the best error, I should say best value that you got, okay, for MAE. So now what we are going to be doing is we are going to simply replace decision tree with random forest. But one of the things that they have said is, it's just funny but it's also true, data science is not always this easy, but replacing the decision tree with random forest is always going to be an easy win. Okay, so we are going to create a random forest model. So we're going to say random forest. First step is define the model, and what is the parameter value? Random state is equal to 1. So we have defined the model. Next is we have to fit the model. So what is our model value? RF, like I said, always copy paste it. It's much easier for you to deal with. What is our training and test value? So it is this. Oops. And finally, can we calculate mean absolute error? Mean absolute error on validation data. So which means you have to calculate it on validation data. So again, to get the name, you can just directly get. Did I even predict? No, we have to predict before that. Predict RF predictions is equal to model dot predict on, I want this to go inside this. Where do I want to predict? I want to predict it on val_x, and I have predictions. This prediction goes here, and then we're going to get the best output. Let's check. Oops, your validation score is higher than. Okay, so if you actually noticed, I made a terribly silly error. Our validation prediction is RF predictions, and I've used the previous one. Correct. So we have got the best random forest error. Like the best value for the error. So previously it was around 27,000. So now we have got 21,000, which is like a delta of around $6,000, which is really good. So far we have followed specified instructions and then try to do something. But it is always good if we learn on our own and then try to implement something rather than just taking things from somebody. So today we learned about underfitting and overfitting. We finished that exercise. Then we learned about random forest, which is again one of the most popular models that you would see. So even if you go to the latest Kaggle survey that was recently published, you would see people still use random forest in a lot of business cases. Random forest and XGBoost, which stands for extreme gradient boosting, are two good models that are used in real world environment as well. So basically you have learned a good thing, but you have to learn a lot of nuances. So after you finish this video, just go to the internet and then start reading about random forest. When will you use it, when will you not use it, advantages, disadvantages. Try with a couple of models in Kaggle competition. But if you're stuck somewhere, I think next video is going to about you trying it in the real world. So let's see. Please let me know your thoughts. If you have any questions, again let me know in the comment section. Otherwise, share your feedback. Am I good, not, anything, whatever. Stay safe, tough times, happy coding.